Welcome back to subtopic 10.4, Application of Standing Wave. The formation of standing wave produced by stress string and air column. For the stress string, in general, standing waves are set up in the string of musical instruments such as guitar and violin when we pluck, bow, or struck it. For the air column, they are set up in the air column in an organ pipe, a trumpet, or a clarinet when the air is blown over the top. So basically, for the air column, we have two types. The first one is the open end, whereby both ends are open. Normally, we call it as the open pipe or open tube. For the closed end type, we have one end open and another end is closed. So normally, we call it as the closed tube or closed pipe. So the first one, formation of standing wave in the stress string. When a string of length L stretched between two fixed ends is plucked and then released, the transverse wave produced travels down towards the fixed end and reflected back. The wave pulse is being inverted when reflected. So let's say we have a string. This is the initial point, s equal to 0. And here is the final point, s equal to the length of the string. And this is the middle of the string. And if we wiggle the string in the middle, the refracted wave travel through each other. This will create a standing wave. The wave and its refraction wave will interfere according to the superposition principle and produce a standing wave. The speed of the wave on the stress string is given by V equal to third T over mu, whereby V is the speed of the wave on the string, T is the tension in the string, mu is the mass per unit length of the string with the formula mu equal to m over L. For a stress string, we can set up a standing wave patterns and many frequency. The more loop is, the higher the frequency is. So next, we have the table showing the mode, standing wave pattern, and frequency of a stress string. So for the first one, fundamental mode, we have the first harmonic with the harmonic number n equal to 1. So this is the drawing pattern of the stress string in the fundamental mode. So we have the simplest standing wave has one note at each end and no more. So we have notes at the end of the string and empty note in the center. So this is the total length of the string, whereby it equal to half lambda. So we can have the relation L equal to half lambda 1. And we can link it to the formula of frequency, F1 equal to V over lambda 1 in general. And we can substitute lambda 1 equal to 2L over here to get the equation F1 equal to V over 2L. For the first overtone, which is the second harmonic, n equal to 2, our next possible standing wave we can make has an additional note in the center. So we can add another note in the center. In total, we have 3 notes. And the total length of the string equal to 1 lambda. So we can write as L equal to lambda 2. So from the formula of frequency, F2 equal to V over lambda 2, we can replace lambda 2 equal to L over here to get the formula F2 equal to V over L. And after we compare formula F2 and F1, we can have a relation F2 equal to 2 times of F1. For the second overtone, which is the third harmonic, we have n equal to 3. So the third possible standing wave has 2 notes in addition to the notes at the end. So in total, we have 1, 2, 3, 4 after we add in another 2 notes here. So the total length of the string equal to 3 over 2 lambda 3. And we have the formula of frequency 3 equal to V over lambda 3 in general. And we are going to replace lambda 3 with 2 over 3L. And we can have this formula. And we can have the relation of F3 equal to 3 times of F1 after we compare with the first formula. So the standing wave on the string forces the surrounding air vibrates and produces a sound wave in the air. If the string vibrating in the fundamental mode, hence the sound wave produced is in the fundamental tone. This is a general equation to describe the stress string, whereby we have Fn equal to Nv over 2L, or we can have the relation Fn equal to Nf1. And this is formula of the speed of the wave in the stress string with the formula square root of T over mu, whereby our mu is a mass per unit length in the unit of kg per meter. And the value of N start from 1, 2, 3, 4, etc. Next, for the formation of standing wave in air columns for both open and closed end. So we have the standing wave can be set up in the tube of air, whereby we call as air column, such as an organ pipe, as a result of interference between sound waves traveling in opposite directions. The relationship between the incident wave and the reflected wave depends on whether the reflecting ends of the tube is open or closed. Let's say we have a closed tube here. So if one end is closed, a node must exist at the end because the movement of air is restricted. So at this part, there's no movement of air molecule. So we have the molecular vibration over this part. And this is a total length of the tube equivalent to 1 over 4 lambda. If the end is open, for example, we have the open tube here, the elements of air have complete freedom of motion and antinodes exist. So at this part, we have antinodes instead of nodes here. And this is the motion of the molecule. So next we have air column open at both ends, which is the open pipe or open tube. So this table shows the first 3 standing wave pattern for a pipe of length L open at both ends. So we have the fundamental mode for the first harmonic, n equal to 1. This is a drawing pattern. The simple standing wave has antinode at both ends and 1 node at the center. So we have antinode at the ends and 1 node at the center. So we have total length of the tube equal to 1 over 2 lambda 1. And this is formula of the frequency we have. F1 equal to V over lambda 1 in general. And we can have lambda 1 equal to 2L over here to get F1 equal to V over 2L. For the first overtone, which is the second harmonic, n equal to 2, so the next possible standing wave we can make has an additional antinode in the center. So beside the 2 antinodes at the end, we are going to add another antinode in the center to make it 3 antinodes in total. And this is the total length equal to 1 lambda. So we can write L equal to lambda 2. And we can have the formula of frequency F2 equal to V over lambda 2. And our lambda 2 equivalent to L here. So we have the formula F2 equal to V over L. And we have the relation F2 equal to 2 times of F1 when we compare with the formula F1. For the second overtone, which is the third harmonic, we have n equal to 3. So the third possible standing wave has 2 antinodes in addition to the antinodes at the end. So basically we have 1, 2, 3, 4 antinodes in total. So the total length will be equal to 3 over 2 lambda 3. And the formula of F3 equal to V over lambda 3 in general. And our lambda 3 equal to 2 over 3L. So we can replace over here for the lambda 3 value to get F3 equal to 3 V over 2L. And next we have the relation F3 equal to 3F1. So based on the table, we can have the general equation Fn equal to Mv over 2L or Fn equal to Nf1. So V is the speed of the sound in the air, L is the length of the air column, and N is the harmonic number start from 1, 2, 3, 4, etc. So for air column open at both ends, all harmonics are present. Next, we have air column closed at one end, which we call it as the closed pipe or closed tube. So this table shows the first three standing wave pattern for a pipe of length L, closed at one end. So first, we have the fundamental mode, first harmonic, n equal to 1. So the standing wave pattern is as shown. The simplest standing wave has a note at the closed end and antinote at open end. So we have antinote here and note here. And this is the total length of the tube and equivalent to 1 over 4 lambda 1. So the frequency F1 equal to V over lambda 1, and we can have lambda 1 equal to 4L, and we are going to replace in this equation to get F1 equal to V over 4L. For the first overtone, which is the third harmonic, we have n equal to 3. So the next possible standing wave we can make has an additional pair of notes and antinotes. So we can have 2 antinotes and 2 notes here. And the total length of the tube equal to 3 over 4 lambda 3. So F3 equal to V over lambda 3. So our lambda 3 equal to 4L over 3, which we can replace over here to get this formula F3 equal to 3V over 4L. And after we compare with the first formula F1 equal to V over 4L, we can have the relation F3 is actually 3 times of F1. For the second overtone, which is the fifth harmonic, n equal to 5, the third possible standing wave has 2 pairs of notes and antinotes in addition to the note and antinote at the ends. So this is the drawing and labeling. And our total length of the tube equal to 5 over 4 lambda 5. And our F5 equal to V over lambda 5. So our lambda 5 equal to 4 over 5L. So we have this formula as written here. And the relation between F5 and F1 is F5 equal to 5 times of F1. So this is the equation in general. Fn equal to Mv over 4L or Fn equal to Nf1. So please take note that the harmonic number of this closed pipe start from 1 and then 3, 5, 7, 9, meaning only odd harmonics are present. So the even harmonic number are missing, which is not found. Next, we have the hints in drawing the standing wave pattern form. Remember the fundamental pattern for all the 3 cases. For the first one, stress string. Second one, open end air columns or open pipe. Third one, closed end air column or closed pipe. So for overtones, use n times f method. Multiply the fundamental pattern according to the corresponding harmonic number n. So let's have a try here. Sketch standing wave pattern for third overtone in the closed end pipe. First step, identify the corresponding harmonic number for the third overtone. So we have the closed end and start from 1, 3, 5, 7, 9. And the first one is a fundamental mode. The second one we call it as a first overtone. N equal to 5 is the second overtone. So our third overtone will be equal to N equal to 7. So next step, divide the pipe into 7 portions. So 1, 2, 3, 4, 5, 6, 7. So step number 3, use N times F and multiply the fundamental pattern 7 times. In step number 4, label all the nodes and antinodes positions. So we have all the labeling, nodes, antinodes, nodes, antinodes. Next, we have example 4, a thread wire of length 80 cm and mass 12 gram vibrates transversely. The wave travels along the wire at a speed 220 meters per second. 3 antinodes can be found in the stationary waveform in between the 2 fixed ends of the wire. First question, sketch and label the waveform of the stationary wave. So since we have 3 antinodes here, so this is the drawing. Question number B, determine the wavelength of the progressive wave which moves along the wire. So refer to the standing wave pattern formed in question number A. So we have the total length of the string equal to 3/2 lambda. So in order to get the value of wavelength, we can simply rearrange the equation to get 2L/3, and we replace the value of length 0.8 meter to get the value of lambda in 0.35333 meter. For question number B, the frequency of the vibration of the wire. So we know that this is F3, so we can have harmonic number n equal to 3. So 3V/2L. So after we substitute the value of V and L, we will get F3 equal to 412.5 Hz. For question number 3, the tension in the wire. So in order to get the tension, we can link it to the formula of the speed. V equal to square root of T/mu, whereby our mu is mass per unit length. So after we arrange the equation, we can have the formula of tension equal to V squared m/L. After we substitute all the value given, we will get the tension value equal to 726 newtons. So this is the end of the video. For example 5, we are going to continue in the next video. Thanks for your watching.